Krispy Kreme, and this is project 2 for hidden instructions.
So the agenda is the motivation, which is the reason for choosing this project, our overview, which is the background and setup and implementation, the results, which is the outcome of the program's run and the code produced, the demo, which is the demonstration of what was conducted and produced during the project, and the closing. So for our motivation, many people do not know that hardware, like software, can be untrustworthy and have bugs. These bugs largely stem from hidden instructions or undocumented instructions on processors, which are less tested or defended due to their obscurity, leading to gaps in security. When an anomalous instruction is executed, it does not execute correctly due to hardware problems or operating system software interactions, such as Windows or Linux. This can be exploited by attackers, obtaining information without authorization or rendering a system inoperable.
So what are hidden instructions? Like previously mentioned, hidden instructions are undocumented instructions found on processors such as those made by Intel or AMD. These instructions are in machine code or assembly, which are executed on the system the processor is part of. Both documented and undocumented instructions have the potential to execute incorrectly, but it is more likely for undocumented or hidden instructions because of their obscurity and lack of testing. These anomalous instructions can be exploited by attackers to obtain hidden information or remove functionality from computers. One of the attack methods is called hardware fuzzing. So what is hardware fuzzing? Fuzzing is a process by which high-risk values are systematically injected into software in order to expose vulnerabilities. High-risk values are combinations of different input values and timings that are likely to cause unexpected behavior and expose hidden instructions. Fuzzing monitors crashes and memory corruptions and traces back the problematic high-risk values to expected hidden instructions.
So for our project overview, for our background, anomalous instructions can be either hidden, undocumented, or documented. To test anomalous instructions, SandSifter was run on 2 processors. After this, a hidden instruction model could be created. For our setup, different processors, including the golden reference model, which is Spike, were run in MobaXterm. Specific files are used to load and test instruction candidates. For implementation, the processor's execution is compared against the reference model to find any differences or errors. Any detected mismatches are analyzed to identify undocumented instructions and flag them for further review.
So SandSifter, we actually ran SandSifter, and we actually found that there were 320,000 instructions over 3 hours. With this laptop, there actually were some issues, so it froze around 8 hours of runtime. And we ran it on the AMD core, and we found 538 instructions over 8 hours. Yeah, the optimized model, the baseline model, we had only tested one hidden instruction per iteration, and the optimized model loads batches of candidate instructions. The Godel model and processor should be tested simultaneously. And as a result, the optimized model is able to run faster and test more possible hidden instructions in a short amount of time. Next slide. So here's the optimized model. And as we can see that the hidden instruction count, we actually begin at 0. And in this case, we actually use an array list instead of actually the previous case where we ended up actually going instruction by instruction. And the advantage of this is that we can directly write to the batch as a batch. And it has improved in several key ways. Firstly, it makes usage of array lists, like I stated, and the model also reads the log file all at once. And what it does is actually saves whether or not the instruction is valid or not in an array. And it's like a dictionary. And so instead of having to open up that log file over and over again, what we do in this case is actually we just index that. Next slide.
So for our demo, firstly, we performed SandSifter on VirtualBox, in which we installed Ubuntu and installed Capstone. And using SandSifter, on Ubuntu, we were able to test the processor and get results by running some Surize Pi to get a summary of the run, as you can see here. And then for our optimized tool, in which we, as we discussed, it had all of the functions of the baseline tool, including using the convert to hex, the check valid instruction, and write instruction to mem functions, on top of using more error catches and also implementing the ability to test hidden instruction candidates in batches. So you can see here the main loop tests random instructions, writes them to memory, and compares the processor's actions to the reference model, just like the original, but it does it in a more efficient and speedy way because of doing it in batches instead of a singular instruction per iteration. Thank you.
So this is a live demo of running SandSifter. This is the folder that you run SandSifter in. So if I open it in Terminal, you can see here that if you run SandSifter, it will begin running this program. And what SandSifter is doing here is injecting instructions, machine code instructions, into your processor and determining which instructions execute anomalously or don't execute correctly, and it records those instructions and summarizes them. So I'll just let the program run for a little bit, and when it gets some incorrectly executing instructions, you'll see how it collects those down here. In my experience, SandSifter takes a few minutes to find any instructions, so it might be a little longer before it finds anything. So what SandSifter is doing now is it finally found some incorrectly executing instructions, which you can see accumulating at the bottom here. It's going through and determining which instructions did not execute properly and are thus anomalous instructions, many of which tend to be undocumented or hidden instructions because they're not as tested and not as protected. So I'll let SandSifter run for a little bit longer here. And to stop SandSifter, you press Q to quit. Typically, one would run SandSifter for several hours or until it completes, but for the purpose of this demonstration, I only ran it for a few minutes. The consequence of this is that when trying to run summarize.py, it goes through the process of creating the summary, but it doesn't actually finish properly, so the summary window does not show up as there's an error with drawing the window. I've only gotten this issue when running SandSifter for a very short amount of time, so I believe that's the reason why, as I've never had that problem before when running it for a few hours. So that's the demo for SandSifter, and I hope it helped to clarify how SandSifter works and how it's run.